Today we're going to talk about the week 8 problem sets. So let's move on to the first question. In this question, Alice and Bob, so Bob is trying to prove to Alice that he is indeed Bob when they are communicating before using RSA protocol. In fact, this is a pretty easy question. All you need to do is that Bob needs to prove to Alice that he indeed knows the signing and verification keys, but not the secret key of signature, and also the secret key for encryption of the message. So all they have to do is to so Bob has to sign. So Bob needs to prove he knows the secret key of, this is a signing secret key, and also the encryption secret key. So if Bob can prove to Alice in front of her, then Alice knows that Bob is indeed Bob. So all they have to do is that Alice first, so they just need to perform the RSA protocol face-to-face, and that actually completes the proof. So Alice needs to choose a secret message and sign it, and then send it as the RSA protocol to Bob, and then Bob decrypt it in front of Alice. Then Alice knows that Bob has the secret message, the encryption key. And then they can do another step that Bob tries to sign a message in front of Alice and then send it as RSA protocol to Alice, and then Alice decrypt it to see that whether the signing key of Bob is actually valid. Then Alice knows that Bob has the secret signature key. So this completes the proof. And yeah, so this is for this question. And for the second question, P is a prime number, and we say that the number G is a primitive root modulo P if all of its powers exhausts all of the elements in 1 to P minus 1. So what it means is that given a G, so G to the power of 1 and then 2 all the way to power of P minus 1, we can map it to some elements in this set. But it doesn't necessarily have to be this order. It can be, for example, A1 could be 10, A2 could be 1, could be, no, not 1, 2, and etc. So this is the primitive root. And if you recall that from the lecture, we have the permutation graph, that we have proven that every permutation graph is consists of a finite distinct cycles with the same length, and we could actually use that use that fact here. So if we want this primitive roots to iterate all of the P minus 1 elements, then intuitively we would want a cycle with P minus 1 length in the permutation graph, right? So if we have a P minus 1 permutation cycle in the permutation graph, if we start at this element, it means that if we start at this element and then we go P minus 1 step all the way to here, So p minus 1 steps, we can go back to our we can go back to the no, it's actually p steps. We could go back to the original elements. Then the p minus 1 step is actually just one element before where we start. So this actually includes all of the p minus 1 elements. So this is a primitive root because it exhausts all of the elements, all of the p minus 1 elements. And let me give you an example. So we know that 2. So if we set a equals to 2, and for the prime number 11, we know that 2 is actually a primitive root of 11. So in the permutation graph, we have 2, 4, 8, 8, 5, then 10, 9, 7, 3, 6, 1, and then back to 2. So this is 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 elements. So it's p minus 1 elements. And you can see that this actually includes all of the p minus 1 elements. So this, if we started 2, we go p minus 1 steps, we will go back to 1, and it exhausts all of the elements, so 2 is a primitive root. And we could use this fact. We're going to so we know that every primitive root, we will have this p minus 1 length cycle in the permutation graph. We can define that the order of the primitive roots is actually p minus 1. And so let me first define what is an order. An order, it means that it is the smallest positive integer such that this element to the power of k, smallest element integer k, so that's g to the power of k equals to 1 modulo p. So this is the definition of order. And we can see that every primitive root has an order of p minus 1, because if we don't have p minus 1 order, then we don't have this cycle, and we cannot iterate through all of the p minus 1 elements. And yeah, that's actually why the order of primitive root is p minus 1. So now I want to prove that for every integer k, such that GCD, the greatest common divisor of a and p minus 1 is 1. With all of this k, the power of primitive roots to the power of k. So g is a primitive root. So this element is also a primitive root. And of course, modulo p. This is also a primitive root. And to see why, suppose for those so given a k, if the GCD of k and p minus 1 is not 1, so it is some number d, then we would have cycles with p minus 1 over d length. And so if we have p minus 1 over, so this, if this d is not 1, so you can see when this d is 1, we have a cycle of p minus 1. So this is a primitive root. But if we don't have this d equal to 1, then this cycle does not have a length of p minus 1. So it has a length, the cycle has a length smaller than p minus 1, then it cannot exhaust all of the p minus 1 elements. So this is not this g to the power of k is not a primitive root. So the permutation graph of this g minus k would look like something like this. So it may have several cycles with the same length, of course, but they're all of this length. Actually, there are d cycles. Then you see that, so this will not. So if we take the cycle that contains 1, the element of 1, and so this primitive root, no. So if we take the cycle that contains, this is the primitive root, and then the power of 2, and then the power of 3. If we take this cycle, then it does not have a length of p minus 1, so it's not a primitive root. And if this d is 1, we will have a single cycle of p minus length p minus 1, and it's a primitive root. So we should count those k. We just need to count those k, which has g, c, d, k and p minus 1 equal 1. So how should we count that? It is just the elements that is smaller than p minus 1 and is co-prime to p minus 1. And this is simply given by the Euler-Tolkien function. So this is why we have this many different primitive roots modulo k. So for f, so if we have a primitive root g, every power of k, which k is co-prime to p minus 1, this g to the power of k is also a primitive root. So move on to problem 3. This is a problem about a quadratic residual modulo n. So an element x is a quadratic residual if there is an a such that this element could be written as a to the power of a squared. And now we let p be a prime number and g a primitive root. Now we should count how many quadratic residuals are there. And this is actually very straightforward. Since we know that for a primitive root, it exhausts all of the p minus 1 elements. So it means that we can map this set to this set. And of course, not in this exact order, but we can map from this set to this set. And if we square all of these sets, so it became like this. So you see that all of this have a quadratic residual, yeah, all of this is a quadratic residual. And because we simply have, so x is equal to g to the power of I squared, right? Since we square every element from above to this. So every element in this set is a quadratic residual. And since we're only taking quadratic residual modulo P, so we should only consider those quadratic residual up to P minus 1. Right. So these are the quadratic residual, and for those left, so this set is actually written as this plus 2 P minus 1 plus 4, and all the way to 2 times P minus 1. So you see that this is actually the same as this one. So we can map, so these two quadratic residual is the same. And similar, this is the same since G to the power of P minus 1 is simply 1, right? It's a primitive root and it has an order, so every primitive root so actually this primitive root is co-prime to P. So by the Fermat's-Little theorem, we have that it's equal to 1. So it's equal, G to the power of 2 is equal to this one, and we can map it to this one, and so on. So we only have to consider here. And how many elements we have here? We simply have P minus 1 over 2, right? Since we are excluding those G to the power of 1 and 3 and 5, etc. So it's P minus 1 over 2. So we have this many quadratic residuals modulo P. And for this set, since we have an odd power, so it's not a quadratic residual. So it is easy to see that. So this is the number of quadratic residual we have. And move on to problem 4. We have a function f is multiplicative if fab equals to fa times fb. And we want to prove that this summatory function, if we sum up all of the divisor of n, and this f is a multiplicative function, if we sum up all of this, is equal to the summatory function. And to prove this, we have to use the fact that, so it's actually a hint to this question, we have to use the fact that if GCD A and B is 1, then every divisor of this A times the product of A and B can be factorized as this, D1 and D2, and which we have D1 is a divisor of A and D2 is a divisor of B. So we have to use this fact. So if we consider an n equal to A and B, oh, by the way, this A and B should be co-prime. So we could actually factorize every positive number of n into a co-prime number A and B. So basically, we could just set one of the element to be 1, and then another to be n. So GCD 1 and n is 1, right? Yeah, so every number can be factorized to a co-prime number A and B. So we would need to prove that this is also multiplicative, this big F of n. So we have Fn, we sum up all of the divisor of n, and this little f is a multiplicative function. We consider the factorization of n into a and b, and then this equals to, since we have the hint that every divisor of a and b can be factorized into d1 and d2, which is a divisor of a and b respectively. So we can just have this d1 that it divides a and fa. No, not fa. By the way, we should also sum up d2. So d2 is a divisor of b, and we sum up, so this d could be factorized into d1 and d2. So this is equal to this one. And then, since this little f is multiplicative, we can write it as this. So we split it. And we would have fd1, and similarly for d2, fd2, right? And if we see that these two are actually the definition of the symmetry function here, right? So we're dividing, so we set n equals to a, and then d equals to d1. We have big F of a times big F of b. So yeah, this actually proves that since fa times b equals to fa times fb, so f is multiplicative. So this proves this question. And for problem 5, let sigma n be the sum of the positive divisors of the integer n. So it's this sum. And we need to prove that this sigma is multiplicative. So it's actually easy. It's actually a special case of the previous problem. We just need to set fd equals to d, and everything else is the same, right? And since this d, of course, this d is multiplicative, so we can set fd equals to d. And if this little f is multiplicative, then its symmetry function is also multiplicative. So we have here this sigma is also multiplicative. And this proves this question. And move on to problem 6. Let n be a positive integer and its prime factorization to be this. We need to find the closed form formula for sigma n based on the prime factorization. So every positive integer could be written as this alpha k, and since every pi is prime, the divisor of, so we take one of the elements out. So if we consider pi to the power of alpha I, this we should consider what is the So we should consider what is the divisor of this pi to the power of alpha I. So since pi is a prime, we should only have pi to the power of 1, pi to the power of 2, etc., up to pi to the power of alpha I, right? So this is all of the possible divisor of pi. Then since sigma n is the sum of the positive divisors of this integer, so we can write sigma. So this is equals to sum of all of the positive divisor as we listed above. So it's from I equals to 0. Actually, I should write from, no, I don't need to write this. So we can see this is a geometric series, right? Geometric series. And it's simply pi alpha I plus 1. And then, so it is this sum, the geometric series. So we can write it as this. And this is for one prime factor of n. And since we proved in problem 5 that sigma is multiplicative, so we have sigma n equals to this. And since this sigma is multiplicative, we can have this. And from the above, for every pi, we have this sum. So we just need to take this product from I equals to 1 to k. And then this sum. So this is the closed form formula for this question. Okay, so for problem 7, let tau n be the number of divisors of n. We have to prove that this tau is a multiplicative function and also find its closed form formula. And so let's first consider n. We should consider its prime factorization, right? So let's first consider the prime factorization of n. This is exactly the same as above. This prime factorization. And now we consider a divisor of n. This divisor is, since this is the prime factorization of n, this divisor can only be, so let's say be beta to the k, beta k, right? Since this is the prime factorization of n. And this beta, every beta should be larger than or equal to 0 and smaller than or equal to this alpha I. Right. So we can see that for each beta I, how many choices do we have? We have 0, 1, up to alpha I, right? So there's actually 1 plus alpha I to choose for this beta I, right? So this tau asks for the number of divisors of n. So for each prime factor of the prime factorization of n, we just need to choose among this many choices for each of this prime factor. And since each prime factor is like independent, so we choose for this many k, beta, we can choose it like this. So it is just number of ways to choose it is just, so we first choose this one. We have this many choices. And then second, so up to the last one. So this is this many choices, right? And this is the closed form formula for tau n. And we have to prove that tau is multiplicative. Since it is actually to prove, we just need to use the result here from problem 5. Since from problem 5, we know that, no, not problem 5, problem 4. From problem 4, we know that if this small f, function f, is multiplicative, then its symmetry function, it's also multiplicative. So go back here. We are counting the number of divisors of n. So it is equal to, like we iterate from 1 to n, up to n. And then we find if, when we're iterating all of the elements, if it is a divisor of n, we just need to add 1. So it is simply, so the divisor should be larger than or equal to 1, and it should divide n. So there's a divisor of n, so we add 1 to it. And this one is actually also multiplicative, right? Because for every a and b, we have this, they're all equal to 1, right? So it is a multiplicative function, and its symmetry function is, as proved in problem 4, its symmetry function, tau n, is also multiplicative. So this proves for problem 7. And for problem 8, we have n and m as positive coprime integers. And we need to consider the set of powers of n modulo n. And we denote it as an. And we say that the cardinality of this an, so we say that the order of n modulo n is on, and it is equal to the cardinality of an. And we need to prove that this order n actually divides the Euler-Toscan function of n. So we want to prove this also using the permutation graph. And similar to the lectures, we can define this mapping. We want to map from x to x times n, m. So we can create permutation graph, since we know this is actually one-to-one correspondence. And so we can have a permutation graph from the lecture. And if you consider for this x, if this x, it's coprime to n, then after multiply it with m, since m is also coprime to n, so after multiplying with m, we also have it coprime to n, right? Because x is coprime to n, and m is also coprime to n. So this xm is also co-prime to n. So we can conclude that in the original set, if x is co-prime to n, then after we map it using this mapping, the result of x times n is also co-prime to n. So after we have the permutation graph, you could imagine that we would have a cycle that all of the elements in this cycle it's co-prime to n, right? Because we map co-prime all of the x that is co-prime to n to another element that is co-prime to n. So every cycle will either contains the elements that are all co-prime to n, or it contains elements that are all not co-prime to n. So the permutation graph we have will be like this. So we would have some cycles that is co-prime to n, and some cycles that are not co-prime to n. Yeah, so this is the so this is the overview of our permutation graph. And if we consider those cycles, possibly we could probably only have one cycle, and we would probably have multiple cycles. If we consider all of these cycles, all of these elements in it is co-prime to n, right? So what is the number of elements in this, set? It's simply all of the elements that is co-prime to n, right? So it's given by this Euler quotient function. And from the lecture, we know that the permutation graph contains cycles that are of the same length. So suppose it has a length of k, and we take this cycle, which has the elements of, so there will be one cycle that has element of n to the power of 2 and m to the power of 3 all the way to m to the power of k minus 1. So if we take this cycle, this is exactly the definition of an, right? Since an is all of the powers of n modulo n, right? So if we take this set, you would have the size of, also this set is an, and its size would be am, the size of an, which is simply the order of n. So we consider this cycle, and this cycle would also contains well, not necessarily contain one, but for this cycle, it would have the length of on. So this k is actually on. And since we have the same length for all of the cycles, so they're all of on length. And since all of this set contain this many elements, so on should divide this, right? So this proves problem 8. And maybe I'm not explaining it clearly enough to you. I'll give you an example. So we are consider n and m to be positive co-prime integers, right? We could set, so it's not necessarily to be prime numbers, but so as long as n and m is co-prime, we're fine. So we set n equals to 2, n equals to 15, and this is not a coprime number. So we need to create this mapping. So F2 maps every x to x times 2. Then we would have F2 equals to, and all of the calculations are in module F. So 1 times 2, 4, 6, 8, 10, 12, 14. And then 16 modulo 15 is 1. And then 3, 5, 7, 9, 11, 11 and 13. So this is our mapping. And we can see 1. So 1 would map to 2, 2 would map to 4, 4 maps to 8, and 8 maps to 1. So 1, 2, 4, 8. And then let's consider 3. 3 would map to 6. 6 maps to 12. And then 12 maps to 9. 9 maps to 3. So this is second cycle. So now we have 3, 6, 12, 9, yeah. And then let's consider 5. 5 maps to 10. 10 maps to 5. This is another cycle. And then let's consider 7. 7 maps to 14. 14 maps to 13. 13 maps to 11. 11 maps to 7. So here are the permutation graph that we get after this mapping. And we can see that, okay, so you see 2 is coprime to n, right? So it maps to elements that are coprime to n. So 2 maps to 4. 2 maps to 4 and 4 maps to 8. 8 maps to 1. 1 maps to 2. So these are all coprime to 15, right? And these are also coprime to 15. And 3 is not coprime to 15. And 6 is not, 12 is not, 9 is not. Also 5 is not, 10 is not. So these are not coprime to 15. And we consider this set since it's either coprime to 15 or not coprime to 15. And for this set, we would have all of the numbers that are coprime to 15. And as in the proof of Fermat's little theorem in the lectures, if A and P is coprime, then after this mapping, our permutation graph would have distinct cycles with the same length. So this is exactly the case. Since all of these elements are coprime to 15, it is simply this number, which is equal to 8. This is simply this number, since we get rid of all of those numbers that are not coprime to 15. So this would produce, permutation graph produces a distinct cycles with the same length, and we have this Euler torsion function equals to 8. And the order, we just need to take n, the cycle that contains n and 1. So it's to the power of 1, to the power of 2, to the power of 3, and 4, right? So this is 2, 4, 8, and since it's modulo n, modulo 15, this is 1. So we take this cycle, it has the order of ON equals to 4, which is a divisor of this value, right? So this is an example for this problem. So move on to problem 9. And for problem 9, we are trying to prove that for every positive integer n, this relation holds. And there's a hint that we should consider the set xt. So we denote xt to be the set of numbers n between 1 and n, such that it has a greatest common divisor with n is d. So this is between 1 and n. So let me write it this way, maybe. This n should be in this set. And the greatest common divisor should be d. This is the definition of xt. Right. So this is the definition of xt. And if we look at this relation, we are asking for the greatest common divisor to be d. But intuitively, we will want to have a coprime number. So we want the greatest common divisor to be 1, so that we can count using the Euler-Tolscher function, right? And consider this value, we could actually write it as this. So this is equivalent to this, and we would have this. So we would have m over d should be coprime to n over d. And no, maybe let me use k. Okay, never mind. Just for now, we use d. So we're counting for since n should be greater than or equal to n, right? So this is equivalent to counting all of the numbers that is coprime to n over d from 1 to n over d. So this so how many elements are coprime to n over d and less than n over d? It's simply given by this. So it's also Euler-Tolscher's function. So it's given by this. And xt is counting for all of the elements in this set that has this relation. And we just proved that this relation is just this relation. And we have xt is the set of all of the numbers that is between 1 and n that has the greatest common divisor with n equal to d. It is equivalent to all of the number of, so this number is equivalent to all of the numbers between 1 and n over d, such that this element is coprime to n over d. So it's given by this value. So we have this set. So from now on, let me use k. We have this set equals to just this number. Right, so this is should be k. So this is what we have now. And if we sum up all of this this set, so you should know that if we sum up for all of the divisor k of n from so maybe let me write it. For all of the k that is greater than or equal to 1, and k divides n, so k is a divisor of n. If we sum up all of such k, and we take the size of the set x k, if we sum up all of such k, it should be equal to the so right now we just prove this, so it should be equal to divisor of n should be equals to this, right? And since each n over k is just a divisor of n, right? Because now we have so here we should have d, right? Because we should have k, right? Should you use k? Should be consistent over this. Since now we have the greatest common divisor of n and n to be k, so if we divided by k, this is also a divisor of n, right? So this is simply a divisor of n because we have k is a divisor of n, then n over k is also a divisor of n, right? So this is a divisor of n, and we can simply write it as, right now we should use d because we're talking about the divisor of n. So it's simply a divisor. So now we prove this relation. And if we think of all of the sets, so if we're counting for all of the sets x1, x2 up to the largest divisor of n, if we count all of such sets, then the union of these sets should be exactly all of the elements in this range, right? Because we're counting for, because this xk is just the set of members, some set of numbers between 1 and n, such that the greatest common divisor n is equal to k. So xk is all of those elements that the greatest common, the GCD is 1. Oh, x1 is all of those elements that the GCD is 1. And x2 is all of the elements that GCD is 2. So if we sum up all of such xk, then so we are iterating through all of these possible divisors of n. So it should cover all of the elements in this set, right? Because for every element it should at least have a GCD with n. So it may be 1 or 2 or k or something, but it must have a GCD with n. So we have the union of all of the k, all of the possible divisor. The union of this should just be 1 and all the way to n. And if we take their size should also be equal. So their size would be, this would be n, and this would be, since we just proved here that the size of xk is equal to this value. So it's just this. And since this is just a divisor of n, we could write like this. It's just a divisor. So this just proves this relation. Yes. So problem 10. We need to prove that every prime number p has a primitive root g. So every prime has a primitive root. So in problem 8, we prove that if n and m are co-prime. So now we are considering those prime number p, right? So every element that is smaller than p should be co-prime to p. From 1 to p minus 1, right? So we can use this proved fact that if n and m is positive co-prime integers, then the order of n would divide the Euler-Toschen function of n. So now we have n equals to p, this prime number p, and m equals to this primitive root g. And for every, no, not n to g. So we can set n to p, then for every n in this set to p, we would have it is co-prime to p, right? So they're all co-prime to p. And every such m in this set, we would have order of m divides the Euler-Toschen function, the value of p. This is from problem 8. We have proven this. And now we have this, and let's denote, so we have a hint here. So let's denote CD to be the set of all remainders that have an order of D modulo P. So we have this, denote CD as the set of all remainders that have an order of D modulo P. And from problem 8, we know that each order D, each such order D should, so here should divide this value. So we have this. So this order should divide the Euler-Toschen value of D. And since P is a prime number, we have this, right? So we have this relation. And if we consider like basically with the same arguments as in problem 9, as I just explained, since CD is the set of all remainders that have an order of D modulo P, and every n in this set should have an order, right? And have exactly one order, not multiple order. So every n in this set should have one and only one order, and it must have an order, and we must have one order. So if we sum up all of such D from so all of the possible divisor, all of the possible order D, if we sum it up, then it would like also be that covers all of the elements here. So we would have the union of the minus 1 order. So we can have order from 1 up to order p minus 1. So the elements that have an order of p minus 1 is actually the primitive root, right? So we can have this, the union of all such CD should be 1 and 2 up to p minus 1. And the sum of the size of all such sets should be this one, right? And it is simply p minus 1. So we have this. We have this relation. And from problem 9, now if we look at problem 9, we just proved that for every positive integer n, if this d is a divisor of n, then if we take its Euler torsion value and we sum all of such Euler torsion value of the divisor of n, if we sum it up, it is actually equals to n. And now we just have p minus 1. We can set p minus 1 as since it is a positive integer. Since it is a positive integer, and every order d, actually, from here, every order d divides p minus 1, right? So we could use the results from problem 9. We have p minus 1 as n, and then we can have this relation. So d divides p minus 1. And it's actually this. So since d is just an order, it's an order that divides p minus 1, we can write this. It's the same as this, right? It's sum up all of such order. So we have this relation, and from problem 9, we have this relation. So we have this relation. It is just the Euler torsion value of d, of such order d. So from here, we actually have the size of such sets CD is just this value, right? Since both of this equals to p minus 1, so we have the size of CD equals to phi d. So we have this relation, and this implies that. So let's consider what is CD. CD is just a set of all remainders that have an order of d modulo p, and phi d is this the number of elements that is coprime to d, and of course smaller than d. So it means that for each divisor d of p minus 1, there are exactly phi d of elements with order exactly d. So this two value, since this two value is the same, so we have exactly phi d order with order 5d elements with order exactly d. So this also implies that if we think of the order of p minus 1, we would have an order of p minus 1, right? Since p is a prime, and this would be equal to phi p minus 1. So it means that the sets of all remainders that have an order of p minus 1 modulo p is just phi d. And since this phi d should be larger than or equal to 1, right? Because we have at least one element that is co-prime to p minus 1, which is 1. So 1 must be co-prime to p minus 1. So this value is greater than or equal to 1. So we have this set is greater than, the size of this set should be greater than or equal to 1. So we have at least one element in this set. So have at least one element in this set, which means that we have at least one remainders that have an order of p minus 1 modulo p. And the elements that have an order of p minus 1 modulo p is simply the primitive roots. So we have at least one primitive root. So every prime number has a primitive root. So this is for problem 10. And that's all for today.